webinar series screen with a Using Additive Manufacturing Effectively title on that title slide. We're a few minutes away from our start time, so we'll give everyone a few moments to get logged in, and typically we see folks logging in as we get started. But if you're seeing the America Makes logo and the TRX webinar series branding there, you're on the right page. So we'll be on silent here for a few minutes until we get started. Good afternoon, folks. For those of you on the East Coast or Central Time, good morning to anyone on the West Coast. Welcome to the America Makes TRX webinar series. We're still a few minutes away from our kickoff at 2 o'clock Eastern, but I see people logging in, so we'll give everyone a few moments to get connected. You should be seeing on your WebEx screen an America Makes slide with a TRX webinar series logo. The title slide is Using Additive Manufacturing Effectively. My name is Scott Deutsch, and I'll be your host this afternoon, and I'll introduce the speaker in the presentation. But if you're seeing that slide, that you're in the right place. If you're not seeing that, connect to us via the chat window, and we can help you get connected. Good afternoon, everyone. We're about a minute or so away from our 2 o'clock start time, 2 o'clock Eastern Time. My name is Scott Deutsch with America Makes, and I'll be your facilitator and host for this afternoon's TRX webinar. Those of you that are still logging in, I see it looks like there's still some people coming on. You should be seeing a TRX webinar series title slide. The title of today's presentation is Using Additive Manufacturing Effectively. If you are seeing that on your WebEx window, you are in the right place, and we welcome you. I'm going to go back on mute just for a moment here until we get to the 2 o'clock hour, and we will start in just a few moments. Hi everyone, once again. The clock on the wall says 2 o'clock, so let's get our today's TRX webinar series started. My name is Scott Deutsch, and I'm the Communications Manager at America Makes, and I welcome everyone that's logged in, and it looks like there actually might be a couple more people logging in as I'm speaking. But I'll take a few moments here and go through some general housekeeping items. First of all, good afternoon. Welcome to the TRX webinar series. A few notes before we get into this. You should be seeing the TRX webinar series title slide. The title of today's presentation is Using Additive Manufacturing Effectively, and we're excited to have our presenters from Fathom with us to go through today's presentation for the TRX webinar series. If you're not seeing that title slide, please send us a note in the chat window so we can get you squared away. At the end of today's presentation, and actually throughout the presentation, there will be opportunity for Q&A. If during the presentation you have a specific question, please do not be shy to post that question in the Q&A section of the WebEx window. We cannot see all the chats that might be taking place, so it's important that you make sure you can find where the Q&A window is in your WebEx screen and post your questions there. That way they're visible to everyone on the panel. Throughout the presentation, we'll be able to see these questions, and we can address them as we go, or we'll get to all of them at the end. We'll do our best to get everyone's question answered. Just a little bit of background about the TRX webinar series before I introduce our speaker. We developed this series to further support the America Makes role as a convener, coordinator, and catalyst for the additive manufacturing community. And we've designed this to be an easily accessible platform that will encourage the users to share their knowledge, the knowledge of what's going on in the additive manufacturing community, and to have these webinars on a continuing basis. In this series, we cover a wide variety of topics related to additive, and we bring together some of the experts out there in the community to present this information. So with that, I'm going to get it kicked off. I see, looks like I'm not seeing any additional people logging in, but I know sometimes people will come in as we go. But with that, I'm going to introduce today's speaker. If we can switch to the next slide. Tony Slavic is with Fathom Studios, and he will be our presenter today in the TRX webinar series, presenting the topic of using additive manufacturing effectively. Tony's been with Fathom since 2011 and is their production manager. He brings some experience in both traditional manufacturing and additive technologies for prototyping and production. And today he's leveraging his expertise to lead Fathom's applications engineering team And we welcome Tony. So I'm going to turn it all over to you, Tony, and let's hear all about this wonderful topic.
Right on. Thanks a lot, Scott, and thanks for having me here today. I'm looking forward to getting into this. So, like Scott mentioned, my name is Tony Slavic. I am the Applications Engineering Manager here at Fathom. I spent a lot of time running our manufacturing operations, and most of my experience with Additive is born of running those operations. And today I'm going to be talking about how Additive is changing the landscape of manufacturing and how it is being leveraged to improve product development and manufacturing in general. With that, we like to frame it with a little bit of history and the current landscape of manufacturing industries. So immediately following the creation of personal computers in the 70s, people tried to create designs digitally, and this heralded the beginning of what's been called the Third Industrial Revolution. And by the 90s, the PC was capable of the computations required for 3D CAD. Today, the workflow for designing and creating products is radically different than it was before this shift. Complex geometry can be created very rapidly, and then immediately the part can be manufactured anywhere in the world with very little human interaction. 3D CAD broke major barriers in communication. The accessibility of these tools put the power to create into the hands of many. However, while manufacturing technology became more advanced and efficient, accessibility of manufacturing has remained a major hurdle for product makers. Now we're seeing a new industrial revolution, dubbed the Fourth Industrial Revolution, or Second Machine Age, or Industry 4.0. There's a few names for this, but this new paradigm comes on the heels of and is intrinsically tied to that previous industrial revolution. It's defined by a range of new technologies that are fusing the physical, digital, and biological worlds, and really impacts all disciplines, economies, and industries. Each of these alone has tremendous potential to affect massive change, but the evolution of these disruptive technologies is moving at an exponential rate and is boosted further by their interconnectivity. The digital world is not only being connected, but it's being created in the physical world through 3D printing. Limitations of what can be done are being removed layer by layer as additive technologies improve in their accuracy, resolution, their materials, and their speed. Additive manufacturing is providing tools to manufacture things that were previously impossible. Also, it is enabling faster and shorter learning cycles as designs are proven and validated more quickly, and customization and on-demand manufacturing are more and more viable. Additive manufacturing is being influenced and influencing the other major disruptive technologies of the Fourth Industrial Revolution. Robotics are enabling 3D printing technologies by expanding the capabilities of existing technologies like FDM. Companies like Branch Technology and AI Build are using robots to print objects on the architectural scale. Taking advantage of the degrees of freedom of these robots, they're able to print multi-axis geometries that are otherwise not possible with existing machines. They're producing 3D toolpaths to create single extrusion lattice structures that are very lightweight and scales larger than any other machine. They are also combining computer vision and machine learning to processes which enable the machine to see what is actually printing and fix errors on the fly. Made in Space is building advanced robotics coupled with additive manufacturing to build structures in space. Project Archinaut sends material and small printer and spacecraft into space to build things like large imaging arrays, space stations, and communication structures. I should say, intending to build imaging arrays, space stations, and structures. 3D printing is also enabling the robotics industry to produce mechanical components and assemblies that would otherwise be impossible. One of the more interesting fields of research is soft robotics. This concept uses pneumatics or hydraulics combined with flexible materials to enable movement. The image on the right is a 3D printed autonomous soft robot called Octobot, produced by researchers at Harvard. It is produced using a combination of 3D printing, molding, and soft lithography. The brain is a 3D printed microfluidic logic controller which distributes the flow of gas to each tentacle. And then the fuel source is a small amount of hydrogen peroxide, which then reacts to produce a large amount of gas within the body to power the tentacles. Artificial intelligence is directly driving 3D printing through generative design. A genetic algorithm can produce multitudes of results that fit the criteria of the constraints and objectives given to it. If machine learning is applied to these algorithms, the computer can take feedback from a human on which solution is better than the others. By collecting and learning from this data, the algorithm can incorporate that feedback into its next iteration of designs and eventually become better at predicting the optimal solution. 3D printing is enabling big accomplishments in nanotechnology. From microstructures with unique mechanical properties to microscopic medical implants. These are created with high precision technologies to deposit materials at the micron scale. The image on the left is a microscopic battery the width of a human hair. It's created using an FDM-like process to deposit conductive materials, creating an anode and a cathode. The image on the right is a fractal truss structure with features as small as 5 microns. In the biomedical field, 3D printing has offered major improvements, especially in medical implants. Implants can now be made patient-specific thanks to CT scans and new generative software. Bone implants can be designed with microporous surfaces, specifically designed for bone tissue to attach and grow within. The same kind of geometry is being used with special additive techniques, using natural polymers to create artificial scaffolding for patient's tissue to grow onto. The image on the left is a 3D printed replacement hip, which is now relatively old. The first one, I believe, was 10 years ago. On the right is potentially the next step in additive. BioLife 4D recently successfully printed a human cardiac patch with the goal of printing an entire human heart. Graduate students from the University of Washington developed a way to create objects that communicate wirelessly directly off the 3D printer. They did this by using conductive plastics and creating springs, gears, and switches that can be used to translate motion into antenna-transmitted information. For example, they created an anemometer which measures wind speed and attached it to a gear. When the gear spins, the teeth connect with an antenna embedded into the object, and that antenna then reflects ambient Wi-Fi signals, which can be decoded by a Wi-Fi receiver. The faster the wind, the faster the gear spins, and the more rapidly those signals are transmitted. They also created a scale and a flow meter that can measure water speed. Material development was critical in the example and is part of very exciting developments in the industry. As they create more designs and take on more complex devices, they're making their designs available to the public. And 3D printing has been affected by advancements in material development, but there has also been major advancements in structuring materials in ways that were previously impossible. The Self-Assembly Lab at MIT has been developing techniques for combining multiple materials that react to environmental factors such as liquids, heat, and even biological elements like sweat to create responsive materials that can change shapes and assemble into new forms. By combining materials with different mechanical properties and specific geometries, they can control how they deform to create a specific shape. Another group at MIT, ran by Neri Oxman, called Mediated Matter, is doing research on combining multiple materials with different functional properties. With technologies like PolyJet, they are able to place multiple materials, pixel by pixel, or more accurately, voxel by voxel, to produce functional gradients and material properties. By placing focus on how material is deposited, this group is unlocking potential in current material sets and moving them further than originally thought possible. The image you see on the right shows white matter tractography, visualizing bundles of axons which connect different regions of the brain. So really, how does this all come together and these tools begin to shape the future of manufacturing? Amazon is an early adopter of new breed of smart manufacturing. Amazon has been working toward manufacturing apparel on demand. The computerized system would include textile printers, cutters, and an assembly line, as well as cameras designed to snap images of garments that would provide feedback on alterations needed in subsequent items. The creation of uninterrupted 3D printing hardware and software platforms is enabling on-demand hard goods manufacturing. With manufacturing on demand comes improvements in factory automation. Tied to the improvements in robotics, machine learning, artificial intelligence, and interconnectivity, automation is becoming more and more attainable on smaller scales and at lower costs. All of this is leading to the ability to provide large-scale mass customization. Mass customization has already been demanded by consumers for aesthetic purposes. But through additive manufacturing, more advanced customization can be achieved, adding shape, color, and even function. The ability to customize geometries on large scales is only just starting to see its potential. Gillette has been piloting a concept called Razor Maker, which uses Formlab's SLA printers on an online portal that allows consumers to shop for an ever-increasing library of handle designs that are then produced on a 3D printer and shipped to the consumer. Far from being just an aesthetic improvement or a way to have ownership of a unique product, additive manufacturing also affords amazing potential in improving people's lives. LimForge is helping patients around the world gain access to customize and configure prosthetics that are printed locally. They help reduce material and equipment operation costs and simplify the supply chain dramatically, helping the patient obtain an affordable solution to what was, until recently, extremely expensive and usually difficult to fit correctly. Combining the manufacturing ability of 3D printers with improvements in software and design tools, LimForge has created a system that will allow for a much simpler and customizable manufacture of prosthetics. This simplification not only reduces costs, but it also comes with improved function and higher levels of comfort from highly tuned custom fits. The old process was onerous at best. You would create a mold, you would cast, you would do a vacuum form, you would fit it, you would assemble it, you would adjust it, and then you would repeat the process. With new measurement tools, the new process can be as simple as scan, then print. With the digital scan and additive manufacturing, prosthetics can be designed and optimized to fit specific purposes for specific people at a lower cost than previously imagined. These are all adding up to a new paradigm within manufacturing. Current manufacturing is struggling to meet these changing demands. Their current production networks are rigid, capitally constrained, and geographically misaligned. Tepid adoption of additive for end-use parts is further hampering manufacturers' ability to respond to these changes in demand. Only about 3 in 10 manufacturers in a recent study by Accenture have implemented key digital manufacturing-related technologies. In order to take advantage of these disruptive technologies and stay ahead of the curve on these developing trends in manufacturing, it's helpful to understand how and when additive can be effectively used. One of the strongest areas of growth in additive is in manufacturing tools. This is a broad subject with a wide range of applications and is ideal for additive given the typical low volumes needed for manufacturing tools. Cycle required a test fixture for physical testing of plugs and receptacles for an electronics assembly. The fixture lasted without breaking for a production run of 10,000, with testing 100% of the parts off the line. 3D printing allowed the fixture to be designed with intuitive function and labeled for ease of use on the production floor. To machine the first fixture assembly, they went through 3 iterations. The estimated price from a local machine shop was roughly $1,600 with a 2 to 3 week lead time. To print the part using an FDM printer, the material cost was $80 and little labor and no programming required. Print time was 28 hours, which allowed them to go through 3 iterations in 1 week, less time than it would have taken to get to the first iteration from their vendor. Solaxis Ingenious Manufacturing is based in Canada and is a tiered supplier in the transportation, aerospace, defense, and industrial sectors. Using FDM Ultem 9085 resin and nylon 12, they were able to iterate quickly and created a high-volume door seal assembly jig that decreased cycle times by 4 seconds. Not only were they able to improve their cycle time, but they were able to 3D print the jig that is over 100 pounds lighter than the traditional jig for this application. And they reduced the design and fabrication time by at least 2/3 as compared to traditional methods. This shrank the overall time from 16 to 20 weeks down to just 3 to 5 weeks. Using additive for this assembly jig enabled Solaxis to continuously improve the jig, saving customers production time and money. In turn, they have increased their reliability of the door seals they provide to the OEMs. This has reduced their compliance issue down to 0, which resulted in higher profits. Another example of using additive for fixtures is an inspection. Oric, a vacuum manufacturer, has regular new product cycles which require tooling for 20 to 30 components that need to be inspected by a CMM and assembled in a production line. The previous process was relatively linear. They would tool up, they would receive first articles, create fixtures, program their CMM, build the assembly pallet, and then release to production. The time it took from receiving first articles to releasing the assembly pallet to production was typically about 30 days. Their new process employs additive by creating all of the components and fixtures while the tooling is being done. This allows them to build the assembly pallet and program the CMM before first articles are received. As a result, their 30-day first article inspection process was reduced from 30 days to just 1 day. Another area of additive that is growing very quickly is end-of-arm tooling. This will only become more apparent as robotics become more pervasive in our manufacturing processes. End-of-arm tooling is also a good example of additive effectively replacing traditional methods to create not only cost savings, but performance enhancements. Depending on what point in a supply chain a robot is being used, the end effector can vary quite a lot. From logistics to production, the end-of-arm tool can be used for welding to gripping. Potential benefits can be more than just a faster, cheaper solution. Design freedom and different materials can show improvements in the end product. You can use lattice or topology optimization to make lighter, stronger parts. Weight reduction can allow for larger payloads and improve cycle time between robot PMs. Integrated components such as vacuum channels, water lines, simplify the assembly and protect things during operation. Plastic reduces scratching when gripping and even dampens impact when tool crashes happen, mitigating some of the risk to your robots. HP worked with an automotive supplier to create an end-of-arm tool to pick up and assemble glass. 4 pneumatic suction cups are directly connected to the printed part's fluid channels to minimize assembly and to protect the vacuum lines from damage during operation. The part was then lightweighted to enhance precision, increase load weight, and increase arm speed. Anubis 3D specializes in, among other manufacturing tools, also end-of-arm tooling. This is an example of a molded end-of-arm tool for large automotive parts. The traditional tool uses heavy and expensive mechanical grippers. In this case, they built a lightweight gripper using a 3D printed body and lightweight cylinder. They integrated Quick Connect for fast swapping. They lightweighted it with an organic structure, and they engineered it for maximum stiffness and used internal vacuum channels for the vacuum cups. Aside from tooling, one of the biggest areas of hype around 3D printing when it began to really gain mainstream recognition was end-use parts. The idea being that everyone would own a 3D printer and would replace or repair any manner of items in their day-to-day lives. The practice of 3D printed parts used in place in CNC or injection molding with no design change, but just a lateral move in the manufacturing method is considered direct part replacement. Used in many cases for bridge to production in low volume, high complexity tooling, this can be a very effective tool, but in many cases it leaves some of the potential of additive untapped. We got through the hype of replacing all injection molded and mechanical plastic parts with additive, and we have, as an industry, defined more clearly where it does make sense to apply direct part replacement. On a project with Mercedes-Benz recently, we worked on designing a new smart tile assembly. One of the parts needed was a simple mount. The original design was just basic CNC mounted, a basic CNC mount as shown in the left image. As we looked beyond the initial prototypes and needed to produce a low volume of production parts, we redesigned it for injection molding. The image on the right shows the redesigned mount with material removed for ease of molding. However, due to a very short lead time and limited time for design validation, we explored the option of 3D printing versus injection molding. We found that the cost of either method was close enough to make either option cost effective, but the added benefits of having only 1 to 2 day lead time for the additively produced parts versus the 2 week needed to get an injection mold made was the deciding factor to go with additive. We built the first 400 SLS parts overnight, and to further reinforce that decision we made, when we assembled the first set, the designers discovered an interference that required a design change, a change that would have ended up being catastrophic had we not just saved 2 weeks by not going to injection molding. But as I alluded to earlier, the real potential in additive manufacturing comes with new possibilities in design that are opened by the additive processes. With that, new design tools are being created and old tools are being revitalized and improved to keep up with expanding potential afforded by additive manufacturing. A tool that has been around for a while but has gained a resurgence in 3D printing is topology optimization. Topology optimization uses physics, stress simulation to generate optimal geometry. A major advantage is that parts are lightweighted specifically for the loading condition they will be under. Lighter parts means less material, and lighter parts also means more efficient assemblies. With topology optimization, typically you get one solution based on your problem setup. With generative design, you can change the question and broaden the problem to get more answers or solutions. This is a definition put forth by Autodesk, and it's worth noting here that the definition of generative design is typically up for debate. With generative design, you, the designer, are able to leverage algorithms and cloud computing to get hundreds of design options. This allows the designer to make the final decision on what to compromise on in your end design. With Autodesk's newly released tool, the algorithms not only take away unneeded elements like in topology optimization, but it will also add elements to make new solution sets possible. Another very interesting design practice, lattice design, is a technique that has been enabled by additive manufacturing. A given design space is voxelized and populated with a lattice unit cell. The structure is then optimized based on the loading constraints applied to the part. Lattice structures have a range of applications, including and not limited to lightweighting, energy absorption, heat transfer, filtration, and medical implants. When these new design tools are applied to the design freedom of additive, the results of using additive become more dramatic. In some cases, function and cost is dramatically improved, and in other cases, previously unsolvable problems are now solvable. Amazon, a manufacturer of industrial farm equipment, looked at redesigning a suspension component prone to damage and replacement. The existing design was limited by manufacturing constraints when originally designed. In conjunction with Altair, a software provider with a topology optimization tool called Inspire, they were able to redesign the component to be more durable. The end result was an increase in durability by a factor of 2.5. They also reduced their weight by 8% and had lower production costs and high flexibility for customer add-on and customization. Andreas Bastian, a researcher at Autodesk, took on a project to redesign an aircraft seat frame. He took the original design and used Autodesk's NetFab to design and optimize a lattice structure that would withstand the same loads as the original aluminum casting. The design ultimately reduced the weight by 54%, which is a fuel savings in the millions and lower carbon emissions. The only problem is the cost of 3D printing in a qualified material at this scale. The solution Andreas came up with was to 3D print the part as a master pattern and cast it in metal. FAA guidelines are very strict on materials and processes, so qualifying a 3D printed part for an airplane can be close to impossible. Casting is already a qualified process with qualified materials. Andreas decided to cast the seat in magnesium rather than aluminum, which is 35% lighter. This process could produce approximately 160 seats every 2 days. The design optimization he employed accounted for 30% of the weight reduction, and the switch of material to magnesium accounted for 24%. Taking an Airbus A380 with 615 seats, if they replaced the seat on a fleet of 100 planes with a lifespan of 20 years, the cost savings would be $206 million. It would also reduce the carbon emissions by 126,000 tons, which is the equivalent of 80,000 cars being taken off the road. The software developer and additive manufacturer Materialize has created a workflow for surgeons to customize 3D printed drill guides for their patients. Then their customized software solution designs a porous structure that mimics bone porosity and is specifically designed to improve secondary fixation of implants through bone on-growth and ingrowth. Of the cases studied with an average follow-up of 2 years, the implant survival rate has exceeded 98%. Leading from that, the current gold standard for implementing additive is utilizing part replacement and optimization to improve designs to the point of consolidating assemblies. This can be achieved in simple assemblies. Normal manufacturing constraints have permeated our design thinking, but as those constraints are removed, we find that many assemblies are easily combined. For example, we redesigned this fan blade housing to work for additive, so it will be combined into a single part and quoted the part price at various volumes. We also took the original design and quoted that for injection molding, which required 3 tools and 6 parts in the assembly. For this particular part, the prices converged around 750 parts. But we are seeing this convergence push out further and further as technologies become faster, cheaper, and more efficient. OPTIZATION is an antenna design company specializing in additive to create highly integrated RF antennas. This particular design was originally 100 discrete parts. OPTIZATION redesigned it for metal additive manufacturing. The end result reduced the part count of 100 parts to 1 single part. It also cut weight by 95%, reduced the lead time from 11 months to 2 months, reduced production costs by 20%, eliminated 75% of non-recurring costs. GE Aviation is working on its next generation advanced turboprops. They took the existing assembly and, leveraging the design flexibility of 3D printing, combined parts and improved performance. The resulting design had 35% of the engine to be manufactured additively, with the original 855-part assembly reduced down to just 12 components. The design also reduced the weight, improved fuel burn by 20%, and resulted in 10% more power. Also, on the manufacturing side, it saved on assembly time, inspection time, certification time. Reliability increased and human error was reduced. Industries such as aerospace and medical are leading to the adoption of additive as a manufacturing method. Due in part to having many high-value, low-volume products, it has been a perfect fit and has shown high returns on investments in the new manufacturing methods. As adoption has increased, prices and technologies have improved, and manufacturers have become more efficient. This trend has been growing in nearly every industry and will continue to grow into the foreseeable future. Thank you very much for your time today. I would be more than happy to answer any questions or discuss some of these case studies we presented, and looking forward to seeing what people bring next to the additive manufacturing world.
Yeah, Tony, this is terrific. I mean, my goodness, I'm not seeing any questions on the Q&A panel here or on the Q&A screen, but this is terrific information. What a wonderful sort of view of 3D printing, its uses, the benefits of it, from whether just starting backwards from part consolidation to the in-process tooling needs of manufacturers, which I think is one of the places that at America Makes, from our vantage point, we see so much taking place. And anybody that's on the call or on the webinar that is an America Makes member, or it has been ever watching what America Makes is up to, you see a lot of the project calls going out that are dealing with a lot of tooling, right? One of the things that you mentioned around, you know, the cost ratios and the benefits for that low volume production of injection molded parts, you know, versus traditionally manufacturing. I mean, that's a terrific, you know, cost break even demonstration there, and we've seen that from others, but what a terrific sort of view of additive and its benefits. If there are any questions, please jump in here and throw them out. And Tony, obviously you've got a lot of work here, and you've got a lot of expertise to share.
For sure. Actually, I see a question that just popped up, and it was to talk more about the micron scale printing and what the technology used is. So the micron scale printing that I'm aware of is being done at research scales right now, and most applications are using modified FDM printers, obviously much smaller printers. The biggest challenges are finding materials that are staying stable at that scale, but as far as I know, nothing has been pushed to a commercial level. There is something that borderlines on the micron scale, and it's a metal printer, and the name is eluding me right now. I want to say Voxel, I think it's XJet. Not 100% sure about that, but it uses a liquid metal. It uses liquid metal in a 3D printer, inkjet print heads, and produces very, very, very small scale metal parts. And it looks like someone just offered up micro FDM company Nscript is also doing the micro scale FDM printing. But Scott, to add to your point, yeah, the pushing into the manufacturing sector is really exciting, and it's not so much replacing injection molding as it's just filling that need of the places where people don't want to spend $100,000 on a tool to make 1,000 parts. And I see this really, really clear cohesion between the additive and traditional technologies developing as more of the processes become commonplace to designers and manufacturers.
Yeah, and to be fair, you know, nobody is most folks that have the understanding of both sort of sides of that technology, or of the technologies, as you demonstrate in your slides, you know, additive isn't going to replace injection molding for those applications where thousands and hundreds of thousands of impressions are necessary. It will fill that need where cost drivers are part of it, and I only need 600 parts. and I may see iteration of my design after the first 200. So it does certainly fill that place. But one of the interesting things in terms of tooling, just as a sidebar, is one of the earliest projects funded through the America Makes program was looking at repair of traditional tooling using additive technologies, because people wanted to realize that, increased yield out of their existing tools, which were manufactured traditionally, but they were getting wear and breakage, and using additive tools to go back in and repair, as you might weld a die or a mold or something, but using additive tools to do that, and then come back in and finishing them off with traditional means. So tooling has been around, and those in the manufacturing world that understand the value of good tooling and how much of a role it plays have seen additives value for a long time. Now, and not to mention the casting world with metal castings of using stand molds or other types of investment castings and things. I mean, you could do 2 hours just on that itself, I'm sure.
Yeah, metal is, so Fathom's focus has always been on polymers, but we run into metal and we work with those. And it's been so much more developed in my experience in terms of processes and specific applications because of the high value. So doing there's really cool stuff with metal casting, or the repairing of tools, or the hybrid machines where you have a company like DMG Mori making direct energy deposition 3D printers it sprays metal powder onto a substrate or builds up from zero, and then has a 5-axis mill that follows up and machines that net shape to a very high precision object. That stuff is a little bit out of my pay grade, but it's super cool to see some of the applications in high pressure seals or some really complex tooling with internalized cooling channels. You can have amazing things happen.
Yeah, oh, absolutely, and with one setup, right? So I've got one operation setup, and out comes my finished part. It is terrific. I see a couple other notes in the Q&A box here. I don't know if you want to try to address. How do you decide on the best AM technology is the one that just popped up, but there was something ahead of that. Otherwise, for the 2 photo nano.
Yeah, for sure. So let's see. So back to the micron scale printing. Someone brought up and just mentioned Nscript, which is a company I'm not familiar with, and I'm going to go look up after this because these opportunities always are for me to learn as well. And also with Nano SLA, which is a company called Microlite or NanoScribe, both of which I have heard of, and they do some cool, very, very, very high resolution things. And some of the more interesting stuff they do is around working with partners, I think, with material development. Whenever you have those thermosets, usually photopolymers with SLA processes, in my opinion, the heavy lifting is really in the material development, because they have to make something that works for the process and then, is an effective end-use part. And there's so much material science behind that I get really excited when a new material gets released. And then there was another question about how do you decide on the best AM technology for producing the part, especially in metal? Where SLM-based solutions are being threatened, my options for HPMJF, FDM, binder removal, and baking, or even WAM. I am usually, metal is an interesting domain. Our conventional wisdom tells us if it looks like it can be machined, it'll probably be cheaper to machine. That aside, you can do some, like I alluded to in the presentation, when you leverage the design freedom of 3D printing and couple that with metal, you can get some amazing solutions. And usually, it's more of a cohesive process to work with your manufacturing process in mind. There's different constraints with SLM or EBM or even some of the more coarse, high feed rate direct energy deposition printing processes that they come with really specific needs, whether it's the stress relief or the minimum feature size that needs to be considered when you're designing it. You end up removing a lot of the constraints of undercuts and internal features, but you do come with some interesting challenges as well. Metal is a deep topic, and there's a lot of softwares designed. There's a new company, man, all these companies I'm drawing a blank on this one too. They just came out with a 3D printer that does metal without supports. It is similar to an SLM process. They're based in the Bay Area, and I'm looking at the person across the table from me wishing she had an answer for me. But yeah, metal processes are Velo 3D, that's the one.
They did it.
Thank you for whoever offered up that answer. I haven't validated any of that. I've heard really good things, and it's an amazing concept. There's also new processes coming out that are dovetailing off of metal injection molding processes that companies like Desktop Metal, HP, and I think probably GE, because they just put billions and billions of dollars into the industry, are looking to replace some of the less efficient manufacturing needs in metal injection molding and investment casting. Let's see. I got another question. How do you encourage more machine shops to integrate additive into their companies? I think my sales team would really like an answer to that. It is, sometimes it's as simple as showing easy wins, but also machine shops, in my experience, have a lot of just tribal knowledge and sort of old school processes, and there's two groups. There's very hesitant to change, and then there's the people who lean into new technologies and love to get involved in them. So I think putting parts in people's hands is one of the most effective ways to prove 3D printing, because it sounds sci-fi to someone who's never used it, and as soon as you show them that it is very simple and easy to use, it can turn a lot of people around in their impression. Usually the harder part with getting a machine shop to use additive is being comfortable using plastics, because most of the applications in a machine shop, in my experience, aren't suited to the metal processes. They're usually too expensive, except for a few of the lower cost options. And people like metal, so convincing them that plastics are strong and you can have benefits rather than just compromise with switching to plastic is a big way to convince them. Things like ergonomics and optimization, so you don't have to make those large, crazy metal assemblies for manufacturing jigs. If you talk to a machinist who works in like an automotive industry, on the manufacturing floor making assembly jigs with extruded metal and chunks of aluminum, and show them a single 3D printed part that required no manual labor other than pressing print, that's a good way to convince them. I've seen that in some of the work we do with Tesla here in the Bay Area. They're a good case study because they like to eschew the norms of manufacturing to their benefit and their detriment. I think
one
that
more question there on the what's the most time-consuming part of the additive journey?
Oh, I got to scroll down. The most time-consuming part of the additive journey, I mean, it usually feels like post-processing. It's anytime you add a step to additive, you're adding costs So my focus when working with people in defining an application and refining it is to not be so intent on adding processes to the whole chain of events. Anytime you need to sand something or polish something or paint something or coat something, it becomes very time consuming. Outside of that, I mean, the machines run relatively hands-free, so it may take 24 hours to print something, but you get to go home and go to bed. So it makes it seem a little bit easier than it is. Let's see. I think that's, yeah, okay, so I scrolled down, found all the other questions I was missing.
Yeah, and absolutely, and I know just from our perspective as well, it's sometimes it's that if you're not already in the digital domain, which is, it depends on where you are in your manufacturing, right? So if you're, usually the first question we arrive at is, what's your file? What are you looking like? What's this look like? Are we able to actually go to print with something, or do we have to create digital for it? So a lot of times when it's a classic part replacement, traditional manufacturing replacement, do we have digital? And that can sometimes be time consuming as well. But yeah, there are multiple pinch points, you might say, or places where you could get hung up, and it depends on the application.
For sure.
Just jumping into your answer there for sure. But,
no, I mean, whenever we do something like this presentation, it's so hard to give a clear-cut answer to anything because we have these multitude of geometries presented, and everything has its own unique challenges, including what process to use, what the post-processing looks like. There's a lot of pinch points.
Yeah, absolutely. I think that's all the questions we got, and we're coming up to about 10 minutes till the top of the hour here. If there's no other questions, I think we're going to wrap it up here, Tony and team, and thank everybody for joining into the conversation and wonderful questions. Great presentation. I'm sure everyone is applauding, even though everyone's on mute. It's a terrific journey and peek into what the industry's up to and what they're doing and some of the benefits of it. Just as we depart, anybody that is on the call that has sat in the webinar today, if you or your company is interested in hosting or presenting during a TRX webinar, please let us know at America Makes. And one little plug here for the NCDMM Summit 2019 in Blairsville, Pennsylvania, which takes place here in just about 2 weeks, 2 weeks from today. It's going to be the theme of this year's summit at NCDMM. So NCDMM is the managing nonprofit that runs the America Makes Institute. So anyone that's interested in defense, manufacturing, or manufacturing in general, advanced manufacturing, this is a kind of a thought space for us to present. But this year's theme is preparing for the next manufacturing revolution. And if you're interested, you see the website there. You can get yourself registered, and we'd love to have you. So with all of that, Tony and team, Bianca, and everyone else, thank you so much for sharing this with us today. And we'll close it out.
Our pleasure.
Yeah, thank you so much. All right.